Why do we believe the things that we believe? Well, in practice, it's usually because either somebody has told us or because we can observe it for ourselves. But how do the people that we rely upon to tell us things know the things that they know? Have they observed them? What about things that can't be observed? Can you observe the Earth going around the sun? Well, if you can't observe it, why do we believe it? And what about things that just aren't the kind of things that can be observed? Will taking modes of reasoning help me to do better in my other courses? Should we raise the federal minimum wage? Is it wrong to eat meat? These are questions to which the answer isn't strictly a matter of fact at all. If we think of facts as being about things that can be observed and proven. Inference is the process of judging that one thing is true on the basis of something else being true. You can also think about that as a process of proceeding from things that we already know to conclusions that we don't already know. Arguments are all about inference. Arguments are all about showing or demonstrating that one thing is true on the basis of other things. But there are a bunch of different ways arguments can go about supporting their conclusions. These are what I call forms of inference. You can, if you like, think of them as different argument strategies, different ways of supporting a conclusion, different ways of persuading an audience. It's important to know the form of inference of an argument because it will help you when you're looking for the reasons or the premises of the argument. If you don't know what the form of inference is, if you don't know how the argument goes about supporting its conclusion, then you might very well miss the reasons because you don't realize that they're reasons. Also, before you can decide whether or not to accept an argument, you need to know how it goes about supporting its conclusion, the form of inference, because the different forms of inference have different criteria by which they're evaluated. Now, there are several different forms of inference which we're going to discuss today. I'm going to be introducing you to them. Some of them we're going to be going into more depth in later classes. Here's a list of different forms of inference. This is not all of the different forms of inference that there are, but it is most of them, and it is the ones that we're going to talk about in this course. The first one is deduction, or deductive inference, or deductive reasoning. Have you ever heard the phrase, putting two and two together? What does that phrase mean? Anybody? Well, when we say putting two and two together, what we generally mean is we take one piece of information and we put it together with another piece of information, and then we draw a conclusion about a third thing. Put one thing together with a second thing, and that allows you to infer a third thing. For example, let's say the mailbox key is missing and only me and my roommate have access to the mailbox key. Well, putting two and two together, I can conclude that my roommate has the mailbox key. You can think of deduction as being like math, but with words instead of numbers. Do you remember doing things like mathematical proofs in high school? Well, that's basically how deductive reasoning works. Deductive reasoning works like this. If one thing is true and another thing is true, then this third thing must also be true. Generally, the first thing and the second thing will be things that you already know or that you already accept to be true. The third thing is something that you don't already accept to be true. That is the power of inference. By putting together things that you already know, you can learn things that you don't already know. Or you can show somebody else that if they believe this thing and this other thing, then they should also believe this third thing, which can function as a means of changing their mind. Here's an example. This example is in the form of what we logic people like to call a syllogism. It's a premise and another premise and a conclusion. I'll remind you that premise is a different word for reason, and I'll remind you that conclusion is a different word for thesis. So deduction works by premise 1 plus premise 2 equals conclusion. Let's look at the example. First premise, a wizard is never late. Second premise, Gandalf is a wizard. Well, if it's true that wizards are never late, and it's also true that Gandalf is a wizard, then what else must also be true? Anybody? Yes, it must be true that Gandalf is never late.
We say an argument is deductive when, if the premises are true, the conclusion must also be true. This is as opposed to non-deductive arguments, where the premises, if true, only make the conclusion likely to be true. In ordinary language, it's common to speak of arguments proving their conclusions, as when we say innocent until proven guilty. But when someone is convicted of a crime, they're not exactly proven guilty. Even if there is, say, video footage of them committing the crime, it could still be an evil twin that nobody knows about. You can't prove it wasn't an evil twin. So in court, we say guilty beyond a reasonable doubt, not guilty beyond any doubt. Even in situations where we demand very high standards of proof, or I should say, very high standards of evidence, the conclusion does not always follow with mathematical certainty. Not like 2 plus 2 equals 4 kind of certainty. Well, a deductive argument is like 2 plus 2 equals 4. Deductive reasoning is like math, but with words instead of numbers. Most reasoning that we use in real life is not deductive, and that's fine. There's nothing wrong with other forms of inference like induction, abduction, etc. Abduction is the name for a type of reasoning, believe it or not. But what makes an argument deductive, what defines deductive arguments and deductive reasoning, is that if the premises are true, then the conclusion must also be true. There is no room for doubt. This is possible because in a deductive argument, the conclusion contains the same information as in the premises, just rearranged. If a wizard is never late and Gandalf is a wizard, that means Gandalf is never late. You're just cutting out the middle term, wizard. Get it?
You're late.
A wizard is never late, Frodo Baggins. Nor is he early. He arrives precisely when he means to.
Now try this. All mammals are warm-blooded. All cats are mammals. What's the conclusion? That's right. Cat equals mammal equals warm-blooded. Easy. Very much like the first example. It even works if you don't know what the words mean. As in this argument, all toves are slithy. All mome rats are toves. Therefore, all mome rats are slithy. Even if you don't know what toves and mome rats are, you know they're slithy. Cool, huh?
Was thrilling, and the slithy toes did gyre and gimble in the wave. All mimsy were the boragos, and the mome rats outgrave.
But now consider this. All cats are mammals. All dogs are mammals. Therefore, all dogs are cats. Uh-oh. Something seems to have gone wrong. Can anyone tell me what it is? Going once? Going twice? Sold. The order of the terms is different in this one. In the first one, all mammals are warm-blooded. Mammals came first in the statement. But in this one, it's not all mammals are something, it's all somethings are mammals. Do you see the difference? The logical relationship between the terms is different. A deductive argument only works if the logical relationship between the terms is such that when you put the premises together, you get the conclusion. The logical relationship lies in what we call the argument pattern. Some argument patterns are valid, others are not. Your book has a list of some common argument patterns that are valid, and you can find them on page 32, I believe. Because it's the pattern, meaning the arrangement of the terms, that makes the conclusion follow or not follow, we can use symbols in place of actual terms, which is what they've done here in the examples of the argument patterns. So any argument that has the pattern, all P1s are P2s, M is a P1, therefore M is a P2. Any argument that has this pattern will be valid no matter what terms we use in place of the letters. Dogs, cats, mome rats, styracosauruses, doesn't matter. Valid means that if the premises are true, then the conclusion must also be true. So like I said, some patterns are valid and some are not. Most are not. Why are certain patterns valid and certain patterns not valid? Well, there are ways to show this, and chapter 5 of your book explains some of them. It explains them by means of logical proofs, truth tables, and so on. Do you remember doing proofs from math class in high school? We had to do proofs in math class when I went to high school. Take the Pythagorean theorem. You remember the Pythagorean theorem. The square of the hypotenuse is equal to the sums of the squares of the other two sides. Now, the Pythagorean theorem has been proven, and in fact, it has been proven in a couple of different ways. Likewise, there are ways to demonstrate that certain argument patterns, like the predicate instantiation one that we just had as an example, there are ways to demonstrate that certain argument patterns are valid and certain ones are not. If this was a class in symbolic logic, I would show them to you and walk you through how they work. But I don't know if you've noticed, but this isn't a course in symbolic logic. This is more of a practical skills course. For our purposes, it's sufficient that you just learn the common argument patterns in the book and remember that they are valid. The assignment that's due next week will help you with that. It's practice. Practicing things is a better way of learning them than memorizing them, by the way. If you're interested in knowing why these particular patterns are valid, you can read about them in Chapter 5, or you can ask about them in tutorial. Now, the arguments that you hear or read mostly will not be laid out in standard form like the ones in the book. But people do use deductive arguments sometimes. So it's good to have an awareness of them and to look out for language like if one thing, then another thing. So in the hypothetical argument that you see here on the slide, it starts off if A, then B, and the second premise is if B, then C. So it is good when you're reading texts and you're looking for arguments, it's good to watch out for language like if one thing, then another thing. Although tip, the then is often left out. People say if there's smoke, there's fire. But that's really the same thing as if there's smoke, then there's fire, right? The then is often left out, but the logic is the same. Here's something that you might see in real life or in a course on social issues. Somebody might say, euthanasia is murder because it is the killing of a person. Well, this is an argument, and we could put it into standard form like this. Premise 1, killing a person is murder. Premise 2, euthanasia is the killing of a person. Conclusion, euthanasia is murder. Right? So we started off with an argument in ordinary language, which was actually an enthymeme, and then we put it in standard form, specifically syllogism. And when we put it in standard form, we are able to see that it has the pattern that we call predicate instantiation. Let me show you. Predicate instantiation is all P1s are P2s. M is a P1, therefore M is a P2, right? And I've sort of put them together here on the slide. All P1s, where P1 is killing a person, are P2s, murder. Killing a person is murder. M, which is euthanasia, is a P1, killing a person. Euthanasia is killing a person. Therefore, euthanasia, M, is murder, P2. Do you see how we made the argument fit the form? We substitute the terms in the argument for the symbols in the pattern. But in order to fit the pattern, we had to add the all. The original statement was euthanasia is murder because it is the killing of a person. Killing a person is murder was the implied premise. But is all killing of a person murder? i.e., is every instance of killing a person an instance of murder? Well, most people would say no. There's self-defense, the execution of criminals, etc. We have to decide, using information in the text and also background information, whether the person making the argument intended the all or not. When they said killing a person is murder, did they mean all killing a person is murder, or did they mean killing a person is sometimes murder? And this makes difference, because if what they intended to say was that killing a person is sometimes murder but not all, then the argument doesn't have a valid pattern and the conclusion doesn't follow. It doesn't have a valid pattern because the pattern of predicate instantiation is all P1s are P2s, not just some P1s are P2s. What do you think the person in this example meant to say? Imagine if the person who said it was here, and you ask them if they meant that killing was always murder or if there were exceptions. I think that when a person normally says this, they mean that killing a person is always murder. All P1s are P2s. In that case, the argument does have a valid pattern, but if you wanted to challenge it, if you wanted to challenge the argument, you could argue that this premise isn't true. This premise, killing a person is always murder. We sort of alluded to that before, right? We don't normally consider cases of self-defense to be murder, and some people believe in other exceptions as well, such as execution for capital crimes. Remember, in order to be successful, a deductive argument has to satisfy two conditions, and you should only accept an argument when it's successful. In order to be successful, a deductive argument has to satisfy two conditions. One, the argument has a valid pattern. Two, the premises are true. All of the premises are true. In a deductive argument, it's only going to be successful if all of the premises are true. This means that if you want to criticize a deductive argument, you can push back on either one of these criteria. If you can show that one of the premises is false, or at least doubtful, then the argument is not successful. If you can show that the argument does not have a valid pattern, then it is unsuccessful. However, on the other hand, this means that if the argument has a valid pattern and you accept the premises, then you also have to accept the conclusion whether you like it or not.
The second kind of inference is called induction, or to be more precise, an inductive generalization. Here's an example. My cat hates getting wet, therefore cats hate getting wet. As you can see, we use inductive generalizations all the time in our everyday lives. You can describe an inductive generalization as using one or more observations to draw a general conclusion about a group of things. To be more specific, you take one or more cases of a thing, cats, and you draw a conclusion about a group or class or kind of things, cats in general. So in the example that we just looked at, there was my cat, and the thing that we were interested in was cats in general. So we made an observation of one cat, and we drew a conclusion about cats in general. That's an example of an inductive generalization. But do all cats hate being wet? Well, we can't really test all cats to see if they hate being wet, can we? That's where inductive reasoning comes in. We use inductive reasoning when it's either impossible or impractical to test our hypothesis on all members of the group. So what we do is we take some of those members of the group, test our hypothesis on them, and then infer that what is true of the members of the group that we actually tested is true of the group as a whole. Science proceeds by inductive generalization. Here's an example. Observation. In a controlled study, we'll talk about what a controlled study is in a later class. In a controlled study, speaking of cats, if you can hear that noise, that is one of our cats trying to destroy the couch. I tried to stop her, but I'm busy recording a video. So sneaky, these cats. Anyway, observation. In a controlled study, psilocybin was found to be an effective treatment for depression in 62 out of 100 subjects. Inference. Psilocybin is an effective treatment for depression. Who knows what psilocybin is? It's okay, it doesn't matter if you know what psilocybin is, but go ahead and look it up after the class. I made up this particular argument, but there really is treatment on psilocybin. Ow. But there really is research on psilocybin as a treatment for depression. In statistics, this method is known as sampling. The sample refers to the set of things that are members of the group that we want to observe, that we want to draw a conclusion about, and the population is the word for the group as a whole. Here's another example. Premise. In a national poll, 52.2% of likely voters said they would vote for Joe Biden in the presidential election versus 41.9% who said they would vote for Donald Trump. Conclusion, 52.2% of Americans will vote for Biden in the upcoming election, and 41.9% will vote for Trump. Okay, so why is this a generalization? When pollsters conduct a poll, they obviously can't ask everybody in the country who they're going to vote for. So they select some number, hopefully chosen randomly, and ask them. And then they infer from what the group that they've sampled says to what the group as a whole would say. Now, whether or not you should accept this kind of reasoning, how much degree of confidence you should have in the sample depends on a whole lot of factors. It depends on factors like the size of the sample. It depends on factors like how random is the sample, or is the sample biased? It also depends upon interesting things like ways that people can fiddle with the numbers or alter the mode of analysis. There's enough here that we're going to be devoting an entire class to how to evaluate statistics and inductive reasoning in general. So I won't say any more about it here. Except I'm going to talk about the statistical syllogism. Whereas an inductive generalization moves from the specific to the general, it is also possible for inductive reasoning to move in the opposite direction. The opposite direction is when we believe something to be true of a group, and then we apply that to an individual. The fancy name for this is a statistical syllogism, and there's an example of it here on the screen. It's called a statistical syllogism because that's really hard to say. No, wait, that's not why it's called a statistical syllogism. It's called a statistical syllogism because it has the same form as the deductive syllogism that I showed you a few moments ago, except it uses statistics. FYI, if this argument here said all students who take modes of reasoning show improvement on essay writing scores, and the second premise, Raheem has taken modes of reasoning, then the conclusion would be what? Yes, the conclusion would be Raheem will show improvement on essay writing scores. However, it isn't the case that all students who take modes of reasoning show improvement on essay writing scores. Instead, we have a statistic. Full disclosure, I made up this statistic. I don't know if there's been any research on how modes of reasoning helps people on their essay writing scores. There's an awful lot of anecdotal evidence, which is to say that me and other people who teach the course have been told that they found it very helpful, especially when it comes to writing essays. But anyway, this is just an example. So let's say that we did some research, and the research showed us that 66%, or approximately 2/3, of students who take modes of reasoning do better on their essays after they've taken the course. Okay, so we accept that to be true, and we also accept to be true that a particular person, in this case Raheem, has taken modes of reasoning So in a statistical syllogism, we infer that what's true of the group will be true of the individual. So we infer that there is a 66% chance that Raheem will show improvement on their essay writing scores.